All right. So welcome to week 7. Yep, week 7. We are in the home stretch. We're over halfway there. We're rolling our way to the end of the quarter. So anyway, welcome. Hope you all had a great President's Day weekend, Valentine's Day. Oh, happy Mardi Gras. Man, there's a lot of stuff going on right now. Anyway, today's plan, we're going to talk a little bit more about confidence intervals. Last time we talked about calculating confidence intervals and kind of what they mean. And we did them specifically for when our variable is a mean, when we're looking at the means of things, the averages. And today I'm going to show you how it's similar, but just slightly different when we want to calculate confidence intervals for proportions. All right, so they're done slightly differently, but it's pretty much the same story. So we're going to talk about that. And then we're going to start looking at why do we care about confidence intervals and confidence levels, and what does that all mean when we talk about hypothesis testing, which is really now where we're going to use stats to tell us, do we believe something is true or not, right? For example, what if I were to say, hey, I just developed this new vaccine that decreases the likelihood that you're going to get COVID by 97%, right? We want to be able to test and see whether or not that's a valid statement, because people can say anything, right? I could tell you that the average amount of money earned by people with math degrees is twice as much as those with sociology degrees. Is it true? No, we have to test it, right? And so that's what hypothesis testing is all about, is looking at statements and going, all right, statistically, do they make sense? If we go out and we sample, does our sample support that hypothesis or not? So that's what we're going to do today. And hypothesis testing is a big deal. In fact, we're going to be doing it pretty much from here on out. So this remaining second half of statistics is going to be looking, now that we sort of learned about these different things like z-scores and the student t-distribution and blah, 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 blah. Now we're going to start using it. Anyway, so that's what's on tap from me. But as always, let me turn it over to you guys first. I know there's some homework due tonight. Are there any homework questions you guys would like to look at?
I was hoping to go over one of the central limit theorem mean problems.
Okay. Do you have a specific one?
Yeah, it's number 1 on my specific. It's just asking for find the probability that the patron's lunch cost is between.
Okay.
And I just keep getting stumped on the between part.
Okay. We can definitely go look at that. Are there any others that people want to see?
I just had a quick question regarding the homework.
Sure.
Is chapter 8 stuff due tonight too?
The chapter 8, that's a good question. What's the topic of chapter 8? I don't know the chapter numbers.
Oh, no worries. Let me pull it up. It's the confidence intervals concepts, and then I forgot.
The first couple of the confidence interval ones are due tonight.
Okay.
The ones that involve means. So I think it's either the first 2 or 3 from that chapter, but then the other ones I bumped being due to next week.
Okay, cool. Thank you.
Yeah, so there should be a couple from confidence intervals. All right. Okay, well, let me go ahead and share my screen. We'll go take a look at the homework here. If I can find it. Oh, there it is. All of my windows open. All right, so central limit theorem mean. And looking at number 1. Let's go take a look at number 1. All right, so obviously this might have slightly different numbers than yours, Carson, but it should be kind of along the same lines.
That's actually perfect. It also has because there's two different problems for the between. It's for a group and for a single
Yep.
selected, and that's what I'm confused on. There's the
Okay.
difference between the two.
Okay. So let's just take a look at this guy. So it says the amount of syrup that people put on their pancakes is normally distributed with a mean of 60 milliliters and a standard deviation of 13 milliliters. I just want to be the guy who does the study, because then you get to hang out at pancake shops all day. That'd be all right. Anyway, suppose that 50 randomly selected people are observed pouring syrup on the pancakes. All right, so let's just start with X. So big X. What does big X mean in this case? What is big X? Let's put it into words. What is big X? All right, so Carson just put in the chat box, mean. It's actually not a mean. What symbol represents the mean? All right, thanks, Willie. Just put in the chat box X bar. So the one with the bar is actually the mean. So when we look at this, the X bar, that's the mean. But again, what is X? In words, what is X? What are we actually looking at a distribution of? All right, so it does come from the population. That is correct. But it's not the population. And here's the deal. I know that we don't actually need to have this to answer the questions and all that, but it's better if we can look at these things and understand what they are in words, because if all they are symbols and we just start putting random numbers in, it's a lot harder to associate those numbers. So let's think about what it actually means. So remember, X is our variable, right? X is the variable. That's the thing that we're measuring. So what is it that we're measuring here? All right, not the average. We're going to find the average, but that's not what we're measuring. So I'm sitting at the pancake shop, right? I'm down at the Red Hut, hanging out, watching people eat their pancakes. If you're not from Tahoe, you won't know the Red Hut. But all right, so I'm sitting at the Red Hut and I'm watching. What am I actually looking at? There you go, Willie. It's the amount of syrup, right? So I'm watching and I go, oh, okay, so Carson just used this much syrup. And Miranda just used this much, and Ashton just used this much, right? I'm going to write down how much syrup did you use. And so that's what X is. X is the amount of syrup that any one person uses. So I've got my little notebook and I write it down. I'm keeping track of X. Okay, well, that's going to help us now fill in the first bit. Right? It says, okay, so X is normally distributed. So the question is, what are the things that are going to go in here? Well, this is the amount of syrup. So what do we know about the amount of syrup? Well, that the mean amount is 60 milliliters. So we're going to put 60 there for our mean. And we know our standard deviation is 13 milliliters. Okay, so that's X, the thing that we're actually looking at, that I'm measuring when I look at every one of you guys that are sitting there eating your pancakes, is how much syrup did you just put on it? Side thought, just think about this. Imagine there's some guy sitting in, the Red Hut with his notepad, just like eyeballing you and watching you. You start pouring syrup and he starts writing a number. Ooh, that's not going to be creepy at all, is it? Anyway, I digress. Okay, so that's X. So then what is X bar? right? We already know that that's a mean. So what is that distribution? When we say we're looking at the distribution of X bar, what is X bar in words? If X is the amount of syrup used by any specific person, what's X bar? Okay, so Willie, just put the amount of syrup for your sample. Close, because it definitely does come from our sample now, right? All right, so Carson just put the 60 milliliters. It could be 60 milliliters, but it's a thing that we're measuring. Again, we should be able to do this in words, just like X was the amount of syrup. And yes, I get all kinds of numbers for that. I'm also going to get all kinds of numbers for X bar. But what is X bar actually? And Willie was close when he said the amount of syrup for the sample of 50. I need one more word in there. You give me one more word and that's perfect. There you go, the average amount. So X bar is going to be the average amount for our samples. So I go out and I sample 50 people. I write down in my book how much they took or used. I take its average. Okay, well, that average, that gets put into my book as X bar. So then I take another 50 people, randomly chosen. I look at how much syrup they use and I figure out the average of that. That goes in my book under X bar. And I keep doing that for a bunch of different samples. So X bar is the average amount of syrup used by our sample group. Okay, so this one, remember when we did the sample or the central limit theorem, there were the kind of the two forms. There was the central limit theorem for means and the central limit theorem for sums. This one is going to be the central limit theorem for means. Because we're looking at over time, if I do lots of samples of 50, I know that those averages for the samples, those sample averages, are going to follow a distribution that is normal if I've got a large number, right? Okay, so what are we going to put into this box? So what is the mean for the sample means? All right, and it's going to be 60 because we saw that the sample means are going to end up having the same mean as the population. So that's still going to be 60. So I'll put that in there. But then what goes into the standard deviation? Okay, so this is where the square root thing comes in. And in general, it's the standard deviation divided by the square root of n, the square root of your sample size. So what Willie just put in the chat box, I don't know if you guys saw it, he just wrote 13 divided by the square root of 50. That's exactly what it needs to be. All right, so I don't know. Well, let me just do it as that. 13 divided by, we'll just see here, square root 50. Negative, it will not. Okay, so we do need a decimal for that. Thanks for throwing that in the chat box there, Willie. 1.8385 if we go to 4 decimal places. All right, so basically what happens is the bigger our group, the smaller our standard deviation, because having a larger group takes care of the randomness, right? It's unlikely that we're going to get a group of 50. If I go in here to the Red Hut and I look at the 50 people that are putting syrup on their pancakes, it's very unlikely that all 50 of them are going to be really strange, right? And be like, oh man, I found 50 of the highest syrup use people in the world, right? That's not very likely. Same thing, I won't find 50 of the smallest amount, all that, where it's quite possible if I just look at one person that comes in the Red Hut, yeah, maybe that one person is one of those kind of freakish outliers that puts, you know, an entire container of syrup on their pancakes, right? More power to them. Right? So that could happen. I might find the one, but if I have a group and the group is of any decent size, like 50, it makes it so that the variation goes down a lot. You can see that here. We went from a variation, a standard deviation of 13 down to 1.8. I mean, huge shrink. And the greater our sample size, the smaller that number gets, which again, should kind of make sense. Okay, so that's what's going to go in here. So now let's look at part C. Part C, if a single randomly selected individual is observed, find the probability that this person consumes between 60.3 and 61.8. All right, well, we're going to be looking for a probability between two numbers. So that should make you think immediately something. What do we immediately know we have to use if we're looking at an interval of values? What kind of command? Yeah, it's going to be a CDF, and it's going to be normal CDF specifically, because this is a normally distributed population. So we'll do normal CDF. You know what? I've got my calculator thing right up here. So let's switch sharing to that real quick. Let me show you how we do that, just to remind you. So if you got the TI-84 or similar, it should be similar to this. So we're going to do distribution. We want to do normal CDF. All right, our lower was 60.3. Our upper was 61.8. Our mean was 60. And our standard deviation was 15. I just want to make sure I got all those numbers right. Not 15, 13. Oops. All right, does that look right? 60.3, 61.8. I think so. Oh, it's because of the plus sign. Darn it. Let's try that again. Okay, so we get 0.0458556, blah, blah, blah. So we'll go to 4 decimal places. That's that 0.0459. All right, so we'll go put that into the homework here. The 4 decimal places. So it's around 4.5%, right? 4.5% probability that somebody's using between those two numbers. Okay, so then let's look at D. It says for the group of 50 pancake eaters, find the probability that the average amount of syrup is between 60.3 and 61.8. All right, well, we're going to do the same thing, right? It's still going to be a CDF, and it's still going to be a normal CDF, but what changes here? What's going to be different this time? So Ashton, when you say the population, what do you mean by that? Okay, so the N. All right, and then Allie put in the chat box, we use the second set of numbers, and that's exactly what's going to happen. We're going to use a mean of 60 and a standard deviation of 1.8385, because now we're looking at the average amount of syrup. We're looking at the distribution of the average amount, and average amount is our X bar. So it's going to look very similar. Let me hop back over to the computer, to the calculator, I should say. Okay, but this time when we go and we do our distribution, so again, still doing a normal CDF. So let me delete that here. So the lower bound is 60.3, the upper is 61.8. We still want both of those. We want a mean of 60. But now our standard deviation is no longer 13. It's now going to be the 13 divided by the square root of 50, so the 1.8385. All right, so let's get that, see what our number is. And it's significantly different, right? I mean, look at those two numbers. The one, just one person being between those two numbers, it was only a 4.5% chance. But if we're looking at our group of 50, there's over 20, I mean, it's a 27%. It's over a 1 in 4 chance. So I randomly go and I do this at least 1 out of 4 times. I should expect to find the average in those two numbers. Okay, so let me go put that number into our homework here. I want to get me some scores. So it was 0.27 something something. I'm trying to remember. Let me go back like 2714. Okay. All right. So does that help a little bit? I'm going to specifically ask you, Carson, because you asked about this one. Does that make a little more sense how to tell which numbers we're using when we calculate our probability? Yeah, okay. Because the other thing that will show up, and I think we saw this on some of the homework questions, was the total amount used, right? So if we were looking at, well, how much total syrup was used by these 50 people, then we'd be using the central limit theorem, but with the sum of the x's. And so we get our mean and our standard deviation a little bit differently that way. For the mean, it's the number n times the population mean. And then for the standard deviation, it's the square root of n times the standard deviation. But we know that we're going to use that one when it's the total amount of syrup. So it's all about the wording, tells you what to do. Okay, so then part D, is the assumption that the distribution is normal necessary? What do you think, yes or no? Because we obviously assumed that this was a normal distribution because we used normal CDF. What we did, or we definitely talked about this, is as the population or as the sample size increases, the more the distribution of the sample means is going to look normal. So sometimes it depends on that n. Do we think 50 is enough? Well, let's just randomly, let's go yes and see what it says. All right. So we just said, was the assumption that it was normal and necessary? And we were told, no, actually, we didn't have to assume that. It actually is normal. And that's because the underlying distribution was normal. So that one actually is no, we don't have to assume that it's normally distributed because it's going to be normally distributed because the population was normally distributed. So that one we can actually go to no. All right, anyway, so hopefully that helps a little bit with your, with the central limit theorem.
I actually have another quick question. I
Sure.
know you like don't know what I'm like exactly like my specific problem, but it's actually like relying on millions or like money. Could I still use this way to solve it?
Potentially. Can you
Okay.
tell me what section it came from, or is this a not your homework but related to something else you're studying?
Oh, no. This is my homework. It's still mean. It's question 1.
Okay, well then let me do this. I'm going to stop sharing for a second because
Okay.
I have the ability to go find your specific one. I just don't need people to see things like people's scores and stuff like that. So, central limit theorem mean. Okay, so got it up. Let me share my screen again real quick. All right, so this look great? Average.
Yeah.
Okay,
Yeah.
so the average production cost for major movies is $63 million and the standard deviation is $20 million. Assume the production cost distribution is normal. Okay, suppose that 7 randomly selected major movies are researched. Answer the following questions, giving you answered millions of dollars, not dollars. Okay, so yeah, this is exactly the same. So what is X this time? In the context of this problem, what is X? In words, what is X? All right, so we have the mean of the dollars from Ashton, and then Allie put in production cost. And then Ashton followed up with production cost with the exclamation. So I think she's with you. But yes, okay, so this one is production cost. So we're just looking at, okay, we're going to go and pick a movie. All right, Forrest Gump. What was the production cost? Avengers, Age of Ultron. What was the production cost? Right? That's what we're actually measuring. Okay. So that one's going to be normally distributed. And then it says the average is 63 million with a standard deviation of 20. So that'll be 63 and 20. Okay. So then suppose that 7 randomly selected are researched. Okay. So X bar, again, is going to be our average production cost for that sample. So in terms of the mean, it's still going to be the same, 63. But what's its standard deviation going to be? It's not 20 anymore. How are we going to get the standard deviation for the means, the sample means? All right, good. We're going to take 20 and divide it by the square root of 7. Right, divide by the square root of n. So when you do that, I got 7.559. So it reduces quite a bit, right? It went from 20 million down to, well, roughly 7.6 million. So we shrunk it again, but that's because we're looking at more than one. The likelihood that we pick 7 random movies that have extreme production costs is unlikely, right? They're going to help balance each other out. For every Avengers movie that costs a boatload to make, we're going to get those indie films whose production costs are really small, and and so like everything's going to kind of average out. All right, so then for a single randomly selected movie, find the probability but it's between 61 and 64. Again, CDF, normal CDF, and we're going to use the first values because it's a single randomly selected movie. And then for part D, same story, except we're going to use the second set of numbers because it's the average production cost for that group, right? And so since it's an average cost, that means it's an X bar. So I guess long story short, can you do the same thing with this, even though we're talking about millions of dollars and it's production costs and it's not syrup? Yep. Yeah, and that's kind of the beauty here, is that it doesn't really matter what the actual things that we're dealing with are, as long as we know means and standard deviations and sample sizes and things like that, we can do the same tests. So that's kind of the power of statistics, really, is that it's like the same thing every time. The same thing can be applied to all sorts of different scenarios and situations. So you really only need to know one thing. Do you know how the normal distribution works? Right? Yes, no, maybe. Well, hopefully you check the box yes, because if you check the box yes, then you can do any one of these. I know you're probably, a lot of you are still on the no/maybe, but hopefully it's coming. And the more we play around with it, the more it'll, the more familiar you'll be, and I think the better it'll go. All right, so cool for that one. Yep. All right. So anything else from the homework, or are we good to keep talking about the confidence levels? Okay, well then I'm going to go ahead and switch screens. I noticed at some point my phone fell down and you're getting to see a lovely view of the ceiling. I will rearrange that here, so just give me a extra little bit and we'll get that set up and I'll meet you back at the whiteboard. Okay, I think we're good. Hopefully everybody can see the whiteboard and see me. Anyway, so let's keep talking about confidence levels and what that means. All right, so again, we're starting to build the how sure are we with our numbers? How confident are we that our means, our proportions, or whatever are the values that we think they are, right? And so we started building confidence intervals that were based on confidence levels. So let me refresh your memory just a little bit, what we were talking about before, right? So the first thing that we always have to do is we have to specify a confidence level. So we're going to say, how sure do we want to be? So anytime you create a confidence interval, you have to have a confidence level, right? 90% confident, 95% confident, 99% confident, but whatever the number is we want. But we have to specify a confidence level. Okay. And so then you may remember what we did is we created an alpha, right? And alpha, that's going to be 1 minus our confidence level. So the way to think about alpha is alpha is the probability that you're wrong. I mean, if you want to think about it that way, that little fishy guy, again, there was the Greek letter alpha. But it's just the probability that you're wrong. So if I say, hey, I'm 95% sure, that means I'm 5% not sure. That's alpha. Or I'm 75% confident. Well, that means that I'm 25% not confident. That's my alpha. Okay, so just think about alpha is, yeah, no, you're wrong. That's not the correct value. It's not what you expect. Blah, blah. All right, so we create the alpha. And then what we did was we split that alpha into two. Right, so we really looked at alpha over 2. And does anybody remember why? Why was it that we did alpha over 2? I know Thursday was forever ago. Why is it alpha over 2? And it's okay if the answer is, I don't know. Okay, thank you, Carolina. So think about normal distribution. Here's another graph of a normal distribution, right? And remember what we're doing is we're making an interval around the mean. So here's our mean. We're going to make an interval around it. So we're looking at in here, the probability that we're wrong, the wrongness can actually happen either on the right or on the left. And so we need that to total the 10%, the 1%, the whatever percent that we can be wrong. We just have to split it into 2 pieces. Okay, so we figure out alpha over 2, and then we determine the error bound. We call that the EBM, error bound of the mean. And that error bound was literally how far can you go from the mean in each direction. And so we create our interval by looking at the mean, and then we add and subtract the error bound mean. Okay, so that was the general process. Now, to do this, we either use inverse norm or inverse t, depending upon if we know the standard deviation of the population or not. Okay, so the other really important thing is, do you know sigma? Okay, so here's the question, should always ask is, do you know sigma? Right, and there's 2 possibilities to that. Yes, we do know sigma, or no, we don't. Now you remember what sigma is. It's the standard deviation for the population. Okay, well, if you do know sigma, we're going to use the normal. If you don't know sigma, we're going to use the student t. And the student t distribution, again, is like the normal distribution. It's not quite the same, approximates it. but it's the one that we use when we don't know the population standard deviation, which is most of the time, actually. It's very rare to know the population standard deviation, but it's very common to have a sample standard deviation because we can just run those numbers if we're given a sample. All right, so in terms of the inverse T, we may recall that some of you guys were like, oh, my calculator doesn't have it. And I forget who sent this to me. Somebody sent me an email, and I've been meaning to put it on the Canvas page of a YouTube video that shows how to program your TI-83 to do inverse T. So I don't know. Was that you, Ali? Maybe Ashton? Okay, it was you, Ali. Okay, that's what I thought. I will be sure to share that. And that way you can get it to do it. I'm also going to put up a chart that has just the values for the t-test. It's a table. It's a little bit more difficult to read and determine because you have to know degrees of freedom and all that sort of stuff. So it's a lot easier if you have a calculator to do it. The other thing I'm going to recommend, and I'm going to put a link to this as well. I'm going to send you guys a link to finding the calculator emulator that I use, right? The one that I show you guys stuff with. You can actually download that yourself. It does have a free trial for 90 days, which will definitely make it through the entire rest of this quarter. And obviously you've seen that it's got an inverse T. So between all those, you should be able to do your inverse T. All right, so here's the process, right? Here's kind of how we broke it down. And this is how it worked for means. So what I want to show you today is how we deal with when we've got proportions. What if what we're looking at isn't a mean, but it's a proportion? All right. So first of all, what does that mean? Okay, well, a proportion as opposed to a mean. Remember, mean means average. So anytime you're seeing the word average, find the average height of a basketball player. Find the average amount of syrup that's used. Find the average, right? We're looking for mean. Proportions, these are percentages. So this would be the 30% of homeowners have a fixed rate mortgage. 62% of people asked believe that chocolate is their favorite candy, right? Or whatever. Okay, so proportions are always when we have a percentage. Now, you've kind of seen this before. There was a distribution that proportions hit on a lot, and that was binomial. Remember the binomial distribution, the yes or no, right? Proportions really are doing, anytime we have proportions, it's the answer to a binomial, right? Is chocolate your favorite candy? Yes or no? Right? Do you have a fixed rate mortgage? Yes or no? Right? And then I can give you the proportion of those people. All right, so our goal is to really do the same thing of creating a confidence interval for proportions, and it's going to be done in pretty much the same way. What you may not remember is that when we create that error bound maximum or error bound for the mean, the little way that kind of the book worked through it is you found a z-score or t-score, depending on which one, and then you multiplied by the standard deviation, and that gave you your error bound maximum. And we have a way for finding the standard distribution for, standard deviation for means, right? We take the sample or the population standard deviation, we divide by the square root of n. or we've got our sample used there. We just have to find it a little bit differently when it's a proportion. Okay, so first of all, some terminology, some symbols for you. We're going to let P be the population proportion. So this is going to be the actual value for the population. All right, so if we're looking at homeowners that have a fixed rate mortgage, for example, the P, whatever percentage, that would be the percentage for the population. Okay, so then P prime, the way that we say this, it's got a little like a apostrophe on it. This is called P prime in words. Or at least that's what I'm going to call it, because that's what we say in calculus. So this is P prime. And what P prime is, this is going to be the sample proportion. So this is the one where we go out and we ask 500 homeowners, do you have a fixed rate mortgage? And they respond however, and I just do the division and I get, oh, that's my sample proportion. You'll also see, depending upon the book or your stats teacher or whatever, another way that you'll see this, instead of P prime, you'll also see it with a little caret symbol over it. This is an alternative way. This one in words is called P hat. So it looks like he's wearing a hat. I'm not making this stuff up, by the way. This is legit math way of talking about this. Statisticians do this. So P hat. So if you ever see this, it means the same thing. It's also the sample proportion. All right. So depending upon who you are and where you've learned it, you can see it both. Okay. So what we need to do is we need to calculate our standard deviation. Well, this comes from binomial. Do you remember, and I know this was forever ago, do you remember how to find the standard deviation for a binomial distribution? And again, it's perfectly fine to answer no. So anybody remember that? Okay, I'm going to take your silence as no. But we had to find P and Q. P was the probability of success, and Q was 1 minus it. All right, cool. Carolina just put it in the chat box. It was the square root of n times P times Q. Okay, so for binomial, we saw that the standard deviation was equal to the square root of n times P times Q. Okay. But our sample proportion, we're dividing by n. We're taking the number of results and dividing by n, which means we need to take the standard deviation for binomial and divide it by n. Okay, so for the binomial, it was this way, but for proportions, we need to divide by n. So you're going to get the square root of n times P times Q over n. And if you just do a little bit of algebra on that, I'm not going to do it to you, but I'll just let you know. That ends up being the square root of p times q divided by. All right, so this is how we're going to actually calculate our standard deviation, but we need these to be our sample values, right? Because that's what we're doing. We're taking a sample, we're finding out these numbers. So in turn for us, the standard deviation, and this is what you're going to want to box. That's the square root of p prime times q prime over n. So that's your standard deviation if we're talking about sample proportions. Right. So again, we're looking at sample proportion. This is the standard deviation of the proportion of samples that we take. All right, well, just to remind you, because you might go, well, I don't remember how to find q prime. Q prime is equal to 1 minus p prime. All right, so this is how we're going to get sample standard deviations. All right, standard deviation of the sample proportions is going to be found this way. So when we create our error bounds, we're going to do it exactly the same way that we did before, which is multiplying this by the correct z-score or t-score. All right. So this time we're going to call it an EBP instead of an EBM. So it's the error bound for proportions. And we're going to find this the same way we did before. We're going to take the z-score of alpha over 2. So we got to cut it in half to allow for the error being on both sides. And then we take that z-score and we multiply by the standard deviation of the sample proportions. And it's this that we then add and subtract to the mean. Or I said mean proportion because we're dealing with it. Whew. Yeah, I know. Wipe that sweat off the brow. It's not that bad. I promise it's not that bad. It's just a matter of putting this in for our various scenarios. But once we figure out what that EBP is, we add and subtract it to the proportion that we got doing our study. So let's do an example. Let me just show you how this works so that you're not quite as terrified as I can tell you all are. I can't see any of your pictures, but faces, but I can tell that you're like, oh, good Lord. All right, so here's an example. Let's say we're going to go and try to figure out what proportion of people paid for college with a loan. Okay, so we're going to go, so maybe we work for the student services department, financial aid at some university. Okay, we want to know what proportion of our students receive financial aid. Okay, so here's what we do. We go and we ask 1,404 people. And we ask them, did you pay for college with student loans? All right, and we find out that 323 of them said yes. So what we want, let's see if we can find a 90% confidence interval for the proportion of people who paid for school with loans. So this is what it's going to look like, one of these problems, and what it's going to ask you. So we want to build a 90% confidence. So basically what we're going to do is we're going to say, okay, I'm going to have two numbers, a small number and a big number. And I'm going to say that I am 90% sure that the actual proportion of people, right? So the population proportion of people that paid for college is somewhere between those numbers. Right? That's what this is actually saying. All right, so here's what we're going to do. Let's start using that 90% confidence interval to find alpha. All right, so alpha, that's 1 minus 0.9, which is 0.1. So I cut that in half, and I get 0.05. So I need the z value that corresponds to 0.05. So you can use your inverse norm, do it on the standard with mean 0 and standard deviation 1. Right, that'll get you the z value. Or the other thing that you're going to find out is that we use this number a lot. 90% is a pretty common one, as is 95%, as is 99%. You're going to learn these z values. You'll just know them because you use them enough. So this one for 0.05 is 1.65. So that's the z-score. To catch 90%, you have to go 1.65 away from the mean. Okay, so that's what's going to go in here, 1.65. We've got this number. So now we need p prime, q prime, and n. All right, well, n is pretty easy. N is our sample size. And so if we look at this, we asked 1,404 people. So there's our n. 1,404. All right, so let's get p prime. So p prime is the population proportion. So from this proportion, or from this population, or sorry, sample proportion. So from this sample, what proportion paid for their student or college with student loans? Well, there were 323 respondents out of that 1,404. So it literally is just take however many people said yes or positive results and divide it by the total number that you sampled. And so this is around 0.23. So 23%. All right, so there's our p prime, which leaves us to get q prime. And that's going to be 1 minus p prime. So 1 minus 0.23, which is 0.77. All right, so here are all the numbers that we need in order to create our confidence interval. So I'm going to erase our question here. We know what we're doing. And let's calculate it down here. So we've got our formula. Let's put in our specific value. So we're going to get our error bound for the proportion is going to equal 1.65 times the square root of 0.23 times 0.77 divided by 1,404. this is purely a calculator exercise at this point, and this ends up being 0.019. All right, so this is what we're going to add and subtract to our sample proportion. So we're going to take 0.23 and we're going to subtract 0.019. Excuse me, 0.211. And then we're going to take 0.23 and we're going to add 0.019, which is 0.249. Okay, so whatever this error bound is, that's what we add and subtract from our sample value. Okay, so here we go. Here is our confidence interval. So I just take my P and I put it between this, and notice that this is P, not P prime, because I'm looking at the population proportion. So what I would say here is that I am 90% confident, 90% sure that the actual proportion of people that paid for college with student loans is between 21.1% and 24.9%. Is it possible that it's outside of that? Absolutely. But I'm 90% sure that it's in here. All right, well, obviously, if I wanted to be more sure, I wanted to create a larger confidence interval. I could increase my confidence level. That would change my alpha, which would change my z's, which would change these numbers. But there's my 90% confidence interval. All right, so it's really, really procedural. You'll notice that it's the same thing every time. We're going to do another one here in just a second. But it's going to be the same thing. It's going to be find all these values, plug them into this equation, add and subtract those numbers. Okay, so zero, the same process all the time. All right, so any questions on this one? Or are we even at a point where you can ask questions yet? Should we see another example and then maybe see if we can answer questions? All right, let's do another one here. So there's a slightly different question, but it's still a proportion question. So here's the scenario for this guy. We go ask 1,898 adults, are dandelions the worst weed in your yard? Okay, so again, this is a binomial thing. Are dandelions the worst one? Yes or no? Okay, and what we find out is that 45% said yes. So this time, let's make it a little bit stronger confidence interval. Let's build a 95% confidence interval. All right. So let's think about the things we need. We need a z that's based on our alpha, and then we need p prime, q prime, and n. All right, well, I'm actually going to start with these things because I think they're a little bit easier. The N is 1898, right? That's how many people we just went and asked. P prime. This time we don't actually have to do any division. We're actually given it. We were told 45% said yes. So P prime here is 0.45. Which means Q prime is 1 minus that, which is 0.55. All right, so we got everything that's going to fit in there. Now we need to get our z-score. So alpha is 0.05, right? If we have a 95% confidence interval, there's the 5% chance we're wrong. So alpha over 2 is 0.025. And so now we need to get the z-score for it. I think I'm going to show you how to do this again with the calculator. So let me share my screen from my computer, because I want you to be able to do this without just having to remember what the numbers are, because you haven't seen them enough to remember the numbers. Okay, so I've got my calculator up here on the screen. So we're going to do an inverse norm. So we go to distribution. We're going to do inverse norm. That's number 3. So we want 0.025 for our area, right? Because we're looking for the z-score of alpha over 2, and alpha over 2 was 0.025. And we're going to use mean of 0 and standard deviation of 1. Okay, so we should be good here. I hit enter. Now this one notice I get a negative 1.9599. That's because I'm on the smaller end, right? I did 0.025. If I had done the upper end, 0.975, it would give me the positive number, but this is all we need, is just the 1.96. Okay, so that's our z-score. So if nothing else, you can always find your z-score this way. All right, let me stop sharing. Come back here to the whiteboard. So this is 1.96. This is another one of the numbers that you're going to see a lot. All right, so let's calculate the error bound for our proportion. So we got our EBP, we're going to 1.96 times the square root of 0.45 times 0.55 divided by the 1,898 people. So we run some numbers on that. My calculator spat out 0.022. So I'm going to take that and add and subtract that to our our sample proportion. So we're going to take 0.45 and subtract 0.022 and 0.5 and add to it 0.022. And so these give us our endpoint. So here's our 95% confidence interval. We're 95% sure that the actual proportion of people who think that dandelions are the worst weed in their yards is between 42.8% and 47.2%. Okay, so hopefully you're seeing that this process is virtually the same as what we did for means. Just for means, we calculated the standard deviation differently because it was a different thing, right? But other than that, it's still the same kind of process. All right, so cool. But again, remember what we're doing here is that when we go out and we sample people, we don't know for sure. Like when we go and we ask these almost 1,900 people, we don't know that their response is typical of a population. We hope it is. But what we do know is that depending on how many people we ask and all that, because of these formulas, we can get a really good idea of how close we are. And this is done a lot. Like I've said, if you go back and you look at what happened in the last year here when we had all the political stuff going on, and you get the polls where they say, oh, 45% of people think blah, and then they say with a possible error of 2% or something like that. That's what they're doing. They're calculating an error bound. That plus or minus 2%. That's this. All right, so anytime you see any kind of a study where they say the average was such and such with plus or minus so much, they were giving you a confidence interval. How confident they are, I don't know that they normally say that, but that's something that they internally decide. They go, no, we want to be at least 90% sure or whatever. They'll set their confidence interval or confidence level, which then helps them figure out their plus or minus. All right, well, you can also use this to go backwards, like in terms of finding how many people you need to ask. Like, what if I was going to do this study? And I say, okay, I want to find out what percentage of people think dandelions are the worst, but I want to be within 2%. I want to be within at least 5%, and so on. You can actually use this same formula to figure out how many people you need to ask. So I'm going to show you that here real quick. So I'm going to put here, how big a sample? How big a sample do you actually need? Well, if you were to take this equation and solve it for n, you're going to get that n is equal to p prime times q prime times z divided by the error bound squared. So I'm not going to torture you with the algebra, but you can trust me. I literally do algebra in my sleep. Has anybody ever had this where I'm going to go off on a little tangent real quick. You ever had a job where like you do the same thing frequently that you like dream about it? Because I know that this has happened to me multiple points in my life. Like when I was in high school, one of my jobs was detasseling corn. I grew up in a rural area. We worked in the field, so you like strawberries and roast spinach and stuff like that. Well, detasseling corn, you do that when you have you're trying to get the right hybrid, and the tassels are the part of the very top of the corn stalk, and it produces the sperm for germination. So you got to get rid of them. So you literally ride on these big machines in a basket, and you watch the corn go by, and you just pop off the tops as they go by. So it's hours of just doing this. Oh my God, I had the horrible nightmares of that happening all the time. Well, same thing happens with teaching. I routinely am teaching class in my sleep. The worst was one time I woke myself up. So I went and got a glass of water and came back to bed. And my brain went, okay, now where were we? And I tried to pick up the lecture from that point. Oh, that was a very, very sad day in Bruce's life. Anyway, So yes, I can do the algebra. It does sound horrible. And I can imagine for some people it's even worse, because I actually like algebra. But anyway, I'm not going to bore you with where this comes from. This is the formula. So notice what we need to know. We want to figure out how big a sample. We need to know, let's start over here in the parentheses. We need to know the error bound. We need to know how good do we want this to be. We want to be within 2%. We want to be within 1%. We want to be within 5%. Okay, we need to know how close we want. That makes sense. We also need the z-score, which means we need to know how confident do we want to be. What's our confidence level? So you need to know how precise you want to be and how confident you want to be in your number. All right, and then we need to know p prime and q prime. So we need to know what is the sample proportion. And then the q prime, we get it from there. Okay, but I want you to think about that. We're trying to determine how many people to sample. And it depends on what kind of proportion we're going to get from that sample. Okay, if that isn't like circular logic, roundabout thinking, I don't know what is, right? I'm trying to build a sample, and in order to build the sample, I need to know how the sample responds. Can't do that. So we have a bit of an issue with this formula. If you go back and you look at the one that we did for means, we didn't run into that problem because it wasn't dependent on the sample. This one is. Okay, so this is when you go, okay, well, crap, what do we do? Well, we're going to use p prime equals 0.5, 50%. And I know what you're thinking. Yeah, but we don't know that it's going to be 50%. That's true. But if we use p prime equals 0.5, this is going to guarantee a big enough n. We might end up being more than we need, right? It might turn out that actually we didn't need that many. But this guarantees if we pick the n that comes from p prime equals 0.5, that one's going to be more than enough to get what we need. Okay, so if you have no idea at all what kind of proportion you might get, use p prime equals 0.5. If you have a little bit of knowledge, like if there have been previous studies done, or, oh yeah, there was a study done similar to this somewhere else, right? You can use those values, but in the absence of any knowledge of anything, just go, all right, I'm going to go p prime equals 0.5. All right, so let me show you an example. All right, so let's say we want a 95% confidence level, accurate to 2%. How big must our sample be? And you notice I'm not asking you or telling you specifically what we're looking at, right? I'm not saying, oh yeah, we're looking at the proportion of people that own cars, or the proportion of people who sleep in pajamas, or percentage of people who shampoo every morning, right? It doesn't matter. It doesn't matter what the question is. All that matters is what confidence level and what accuracy do we want. All right, so check it out. Here you go. We're going to have n equals, so p prime, we're going to use 0.5 because we don't know anything about this. Q prime, well, if p prime is 0.5, then q prime is 0.5. 0.5. All right, we need the z value that corresponds to our confidence level. Well, the 95% confidence level gives us an alpha of 0.05. So it's the alpha that corresponds to 0.025, which is the one that we just did when I did it on the calculator a second ago. And that was a 1.96. And then we look at our error bound. Well, we want to be within 2%. So my error bound is going to be 0.02. All right, well, we run the numbers on that, and rounding up to the nearest whole number, because remember, n is is the number of people that we're asking. I can't ask decimal values. This gives me 2401. So I got to go out and ask 2,401 people to be sure that I'm going to be accurate within 2% on a 95% confidence level. Okay, so can I explain? Yes. So why do I have 0.5 for P and Q? Okay, well, the P, the 0.5, it's just because how the numbers work. That P of 0.5 guarantees you the biggest possible value. Okay, the way you could actually see that is by playing with different P values and kind of seeing what's going on. If you actually want to prove it, you need to use calculus. But the 0.5 guarantees the biggest n. And then why Q prime is also 0.5 is Q prime is 1 minus P prime. So if we do 1 minus 0.5, that's also 0.5. So I don't know if I answered it to your satisfaction. Who was that, Allie? Because I know why I choose P equals 0.5. I kind of have to give you a dad answer right now because it works. But mathematically, choosing P equal 0.5 is going to make this the biggest possible number. And if it turns out we don't need this many people, if we ask this many people, we've at least hit our target, right? We would hate to choose and ask 2,401 people when we really needed 2,408, right? And now we're not good enough. So that's why we shoot for the biggest n. If we're going to make an error here, or if we're going to do anything, we're going to overshoot to make sure that we've got how many we need. Okay, so the P equals 0.5 is just because it makes it biggest. And then the Q equaling 0.5 just comes from Q prime equaling 1 minus P prime. So hopefully that's good enough. If not, we can chat in office hour or something maybe, and I can help explain it better. I mean, crap, if you want, come to my office hour and I'll show you the calculus. So when you multiply, that makes 100%. When you multiply these two by 100, you get their percentages, and they add up to 100%. Yeah, I think that's what you're asking. I like to think of them as decimals that add up to 1, but percentages that add up to 100 is also okay. But when you multiply them directly together, you do not get 100%. When you add them together, you get 100%. All right, well, let's just change this slightly. Suppose that we're doing a study. Now, let me just tell you, we're doing a study. Maybe we're looking at the proportions of homes that have a desktop computer. Okay, not a laptop, not tablets, phones, but an actual desktop computer, like at the school and stuff like that. Okay, so maybe that's what we're actually curious about. And we found a study that said, hey, you know what? 40% of homes have a desktop computer. So we could adjust this and say, all right, well, what if we know the p-value? So same story, but suppose we know p prime equals 0.4. Let's see how that changes the n. So n should go down, because remember I said by using the 50% of 0.5, we're guaranteed our biggest possible number. So we should get a smaller number here, but let's see how much smaller. Okay, so now n is going to be 0.4 times 0.6. Right? These two numbers are now 0.4 and 0.6. They add up to 1. But then the other pieces are still the same. There should be a square on that one. So I'm still going to take 1.96 divided by 0.02 and then square it. But this time I'm going to multiply by 0.4 and by 0.6. So if you do this, you end up with, and again, round it up to the nearest whole, you get 2,305. So it is smaller, right? It's a smaller number. I don't need to test nearly as many people. But I had some other information ahead of time. I knew something about the likelihood of the sample proportion. But that's why it doesn't actually matter. You can always just jump to the 0.5 for p. And well, if I asked 2401 and it turns out I only needed 2305, at least I've still asked enough people. But you can see in the real world, it would be better if we could be more accurate. We already knew a little bit. Because if this was, you need to call this many people, I got to pay folks to call and ask an extra, what do we have, 96 people? Well, that's going to cost more money. And so in the real world, yeah, maybe we want to be able to not have to do that. All right. Well, anyway, so there are your confidence intervals for proportions, and they're very similar. Confidence intervals for mean. We just calculate our standard deviation in a different way. All right, well, hey, let's take a quick break. I see on my clock that it's 5:11. Let's come back in like 9 minutes. We'll come back at 5:20. I just need to stop talking here for a second. And then we'll move on to hypothesis testing, what it is and how it has to relate to confidence intervals. Okay, so you'll know I'm back when you see me live again. All right, so see you in just a few minutes. So I'm back. Let's talk about now testing the validity of statements. All right. So again, let's say I work for a drug company and I create this new wonder drug. I think is amazing because it's going to decrease the likelihood that, or it's going to decrease the amount of time that it takes for your body to fight off cancer. All right, so you get diagnosed with cancer, I give you this wonder drug, and maybe I tell you, okay, it's going to shrink tumors by 20%. Okay, so I make this statement. We need to be able to test it. We need to be able to look at a statement like that and go, is it reasonable? Does it make sense? Are they correct? Right? So the way that we do that in stats is with this thing called hypothesis testing. So it's spelled hypothesis, but we say hypothesis. All right, so hypothesis testing. All right, so here's basically what we're going to do. We are going to make a statement. And I'm going to put here in parentheses guess, because sometimes I like to think about it as a guess, but we're going to make a statement regarding whatever, the effectiveness of our drug, the time spent in traffic, whatever. Okay, we're going to make some sort of a statement. We call this a hypothesis. Okay, so we're going to make our hypothesis. So after we do this, after we make this conjecture, we're going to use stats and test it with samples. All right, so maybe this is we think that this drug reduces the size of tumors. So I'm going to go out and I'm going to go sample a bunch of people with tumors that have taken this drug, and I'm going to see, what has happened to these people under there while taking this drug. I need to look at that sample and go, does it appear that this statement is correct? Right? Is it correct? Is it not correct? Well, I can't actually answer that with my sample, but my sample can tell me whether or not it seems correct, or no, that doesn't seem right. Okay. Remember confidence intervals? It's kind of the same idea. How confident are we in being able to reject this hypothesis? How confident are we that it's actually correct? So we are going to have to specify a level of confidence, just like with confidence interval. But somehow we have to test it with our sample. Okay, so this is the general process. Now, some terminology for you. There are two types of hypothesis that we use. Okay, we use one that's called the null hypothesis. And we represent that with an H with a little sub O. Okay, so that O is written as a subscript, kind of like an exponent, but in reverse. Okay, and this is our null hypothesis. And for every null hypothesis, there's also an alternative hypothesis. And we're going to use H sub A for that. Okay. So when we do a hypothesis test, we actually always make two hypotheses. One that's called the null and the other one that's called the alternative. Okay, now, the thing about the null hypothesis is that the sample is the same as the population. And when I say that the sample is the same, I mean that the statistic that we get from the sample is the same as what we're looking at in the population. Okay, so the null hypothesis is saying our sample represents the population. Okay, the alternative is it is not. No, it's not the same. Okay. So these are two competing hypotheses. Right? You can't be in both. You're either in one or the other. So when it comes down to it, it's going to appear that either the null hypothesis seems right or the alternative hypothesis seems right. And we're going to pick one of those. All right, so in terms of how these are built, let me kind of show you how these are going to look. All right, so for example, let's say that we create a new additive that we believe extends the life of car batteries. And I'm going to figure from the current average of 36 months. All right, so we work in a lab, chemistry, we'll come up with this great thing that we realize that if we put into the batteries, actually makes them last longer. At least that's what we think there. Okay, so here's how we would write the null hypothesis and the alternative hypothesis using math. Okay, so the null hypothesis is going to be that the mean is 36. Our alternative hypothesis is going to be that our mean is greater than 36. All right, so let's look at how this got built. So I think that I've got something that makes them last more than 36. So I want a hypothesis that says the average lifespan is greater than 36. That has to go into the alternative hypothesis because it's not the same. Remember that null hypothesis is always the sample and the population are the same. So our null hypothesis would be, yep, the mean equals 36. Where the alternative is the mean is greater than 36. In some books, some people will actually make this less than or equal because those are all the options that are not 36 or not greater than 36. But I'm always just going to write it as equals because that's how I learned and it doesn't really matter. I'll show you why in a minute when we get to the using the calculator to do this. But here are the two hypotheses then. The first one is, nope, there is no change. Putting in this additive, oh well, doesn't do anything. The other is, yes, the additive increases the lifespan, but makes it greater than 36. All right, so there's an example. Here's another example. Let's say we've got a medication. And so this new medication claims it does not change heart rate. And I'm going to just put here which averages 82 beats per minute. Okay, so average heart rate is 82 beats per minute, and this pharmaceutical company comes out and says, hey, this new medication we got doesn't affect it. All right, well, here are your two hypotheses. So the first one is going to be, again, the mean is 82. The alternative is going to be the mean does not equal 82, because we're not concerned with greater than or lower, right? They just say it doesn't change it. It doesn't equal 82. So your null hypothesis is always going to be easy. It's just going to be the mean is what we're given. The proportion is what we're given. It's the alternative that we need to think about. Is it greater than? Is it less than? Is it not equal to? You're always going to have one of those three. Greater than, less than, or not equal, and the wording will tell you. Right? Like this one, the first one, since we thought that it extended the lives of the battery, we wanted greater than. If it had been, we think that it decreases the size of tumors, it'd be less than. Changes, not equal to. Not equal. All right. So there are your hypotheses. As we play around with these, I think they'll make a little more sense. But the null hypothesis is always equal to, and the alternative is either not equal to, greater than, or less than. All right, now when we do hypothesis testing, we only ever talk about the null hypothesis. So only two things can happen. Okay, so only two things can happen in hypothesis testing. The first is that we reject the null hypothesis. We say we don't agree with the null hypothesis. So like for this one, the null hypothesis would be that the average rate of heartbeats is still 82. And we might go, no, that doesn't feel right. I'm going to reject that. The stats don't agree. So we can reject the null hypothesis. What that means effectively is that the alternative hypothesis appears correct. Okay? But what we're going to say is we reject the null hypothesis. Well, if I reject this thing, then it makes the other thing seem plausible. Okay, the other thing that we can do is we can fail to reject the null hypothesis. And I want you to look at the wording. I'm failing to reject it. I'm not accepting it. I'm not saying, oh yeah, that's right. What I'm saying is, I can't say that that's wrong. It's the weirdest thing, right? But this is what we're doing when we do hypothesis testing, because we're never sure. Never sure. We can't just say, yeah, no, we accept the null hypothesis. Instead, what we can say is there's not enough evidence to reject it. Okay, well, what that means effectively is that it appears that the alternative hypothesis appears correct. But the actual words we say, we either reject the null hypothesis or we fail to reject it. All right. So here's the deal. Let's go with an example where we've got a hypothesis, and we can talk about what it means to either reject it or fail to reject it. And let's think about like in a courtroom. Okay. So for example, let's say that here's our null hypothesis, is that the defendant is guilty. Okay, so we got somebody on trial, and our null hypothesis is the defendant is guilty. So that would make the alternative hypothesis the defendant is not guilty. Right? So think about what we said before. The null hypothesis is always an equals. So in words, that would be an is. So the defendant is guilty. So the alternative is, what's the other possibility? Not guilty. So here's what's going to happen. Think about in a court. Now, you may have never been in a court, but you've probably seen, court procedurals on TV like Law and Order or things like that, right? So think about something like Law and Order and court show. You've got your judges and all that. So we got the defendant. A case is made. Evidence is shown, is presented to the jury, and then the jury makes their decision. Okay, well, in stats, we're going to have evidence. That evidence is going to come from a sample, from a study, whatever. So we're going to get some information. And then we're going to use that evidence. We are the jury. And we're going to look at that evidence and go, oh, you know what? I either am going to reject the statement. I'm going to say, I do not agree with the statement that the defendant is guilty. In essence, I'm saying, I think that they're not guilty. I think they're innocent. Okay, so I'm going to reject that hypothesis. Or I'm going to look at that evidence and go, you know what? There's not enough evidence to reject this. There's not enough evidence for me to say the defendant is not guilty. So that makes me think that they are guilty. Right? So that's the difference. We either think that the alternative hypothesis appears correct or the null hypothesis appears correct. But we're going to say reject HO or fail to reject. All right, but we could be wrong. And in trials, we know this happens all the time. That there are innocent people that are found guilty. There are guilty people that are found innocent. Right? So mistakes can be made. And in the context of statistics, we have names for those kinds of mistakes. All right, here are like really the four things can happen. All right, let's do this. Suppose that we've got the options here of the null hypothesis is correct. And the null hypothesis is incorrect, right? Those are both possible. If we think about it, a person who's up for trial, they're either guilty or they're not guilty. And if we think about our two possible choices, we can reject HO. We can reject that null hypothesis. Or we can fail to reject. So there are really these 4 situations. All right, now if we reject our null hypothesis and the null hypothesis is incorrect, this was a good choice. This would be saying we find the defendant not guilty when they really are not guilty. Okay, good. Similarly, if we fail to reject HO, so think HO sounds right, and HO is correct, this is also a good choice. Because this would be the defendant is guilty, and we refuse to say that they are innocent. Right? That's okay. If you're guilty and I say, I don't have evidence to say that you're innocent, that's actually still an okay thing, right? There's no error there. But these other 2 lead to errors, right? Like think about this one. The defendant is guilty, but we go, oh, we don't think the defendant is guilty. That was a problem. Now we've got a criminal who got to walk. They're not getting punished for their crimes, right? So this is an error. And the same thing over here. This one would be the defendant is guilty, or sorry, the defendant is not guilty, but we don't say you're not guilty. That's also a problem because now we've got an innocent person who's going to jail, right? So that's another kind of error. So basically, there are, of the 4 different combinations, half of them are problems. So clearly what we're going to try to do is minimize these errors. But these errors are also very different. Like just think about this guilty innocent. There's a big difference between sending an innocent person to jail as opposed to letting a guilty person walk free. Those are both mistakes. Those are both problems, but they're problems in different ways. Okay, so statisticians, of course, say, well, these errors are not the same. So we say that this first one is a type 1 error. So that's letting the guilty person go free. The other one, we call this a type 2 error. And that would be the putting an innocent person in jail. Okay, so we got these 2 kinds of errors, type 1 and type 2. All right, so because we're like this, mathematicians want to talk about what's the probability of these different errors occurring. And so we're going to use alpha. This is going to be the probability of a type 1 error. Okay, so that's the probability of letting the guilty person go free. And we're going to use this guy, kind of a curvy B. This is a beta. It's the second letter in the Greek alphabet. Right, like the fish, the beta fish. Beta, this is going to be the probability of a type 2 error. All right, so those are just the probabilities, alpha and beta. And what we do when we're doing stats is we try to minimize alpha. All right, we set alpha and we call this the level of significance. So it's sort of like the confidence level, right? When we made confidence intervals and we said, okay, I want to be give a confidence interval at 90% level. we're going to do sort of similar things. We're going to say, okay, we want a 5% level of significance, meaning we only want a 5% chance of a type 1. Or I've got a 2% level of significance. Alpha is 2%. I only want a 2% chance of a type 1 error or so. All right, so for every hypothesis test, we have to state how sure we are, how confident we are, or how much of a mistake we're willing to make. All right, so let me give you another example. The innocent, guilty, I think kind of helps, but let's do one that's more like statsy. All right. So here's another example of something that you might see, and let's think about what the type 1 and type 2 errors mean in this case, right? With the guilty person, it was the guilty person goes free, or the innocent person goes to jail. So here's another one. Let's say here's our null hypothesis. And this is that there's a drug that is safe for children. All right, so a child can take this medicine and it's not a problem for them. So let's think about what the different kinds of errors are. So type 1 error would be that this is true, but we reject it. We think that it's not true. Okay, so a type 1 error would be that the drug is safe, but we don't give it to kids. All right, so that's what that means. The drug is safe, but we don't give it to kids. Right? So we did our study and go, oh man, it definitely looks like the drug is bad, so we're not going to give it to kids. When in reality, we could have been fine. We just don't give it to them. Type 2 error would be that the drug is not safe, but we still give it to them. Okay, so now our null hypothesis is not correct. So the drug is actually not safe. But we didn't end up rejecting it. I don't know, it looks like it's fine for kids. Let's go ahead and give it to them. So you can see that these are very different problems, right? Like in the real world, think about what this is. The type 2 error, we're killing our kids. We're giving them something that's not safe for them. Where a type 1 error is, well, we're just not giving them something that could have been beneficial. It's a very different kind of error. So depending on what you're doing and who you are and how the null hypothesis is set, you want to try to minimize one or the other. You can't minimize both. The less likely you are to make a type 1 error, the more likely you are to make a type 2 and vice versa. So it's usually a balancing act, but there's usually one of these that's better than the other in terms of actual results, right? And I think this one definitely helps show that. All right. Looking at my clock, we're pretty much out of time. So I'm going to go ahead and stop here. On Thursday, we'll pick up where we left off. So we'll start actually doing hypothesis testing. We'll look at some situations and we'll see, what, how we determine whether or not we reject the null hypothesis or fail to reject it. But before we do that, we're going to have a quiz. It is quiz day. Thursday is quiz day. And this quiz is going to be on chapter 7 and 8. Okay, so quiz Thursday, on chapter 7 and chapter 8. And I will just tell you for chapter 8, I'm not going to do any of the bit on proportions. That's what we talked about today. So I'm not going to have you do calculate confidence intervals for proportions, but there will be things about confidence intervals of means. Okay, so the first part of chapter 8. So we'll have a quiz on Thursday. So like normal, go in there at 3:30. It'll be accessible on Canvas. Make sure you get it uploaded by 4, and we'll start in here at 4 o'clock. All right. So other than that, make sure you do all your homework because homeworks are due tonight. So I think with that, I'm just going to tell you, hey, have an awesome couple of days, and I will see you on Thursday.